Right, guys, today we're going to be discussing the Bohr model of the atom and light. So, at the end of the 19th century, there was a bit of a revolution going on in physics. No one knew what anything was anymore, and so part of that is sort of new developments of how our understanding of the world works. So, Niels Bohr developed a model of the atom that involved electrons circulating the nucleus in fixed orbits, sort of like the sun with the solar system. This was a modification which of the nuclear model, but one of the key things here described is the orbits of the electrons. Um, he basically stated that the the electron here that's orbiting the nucleus can only occupy certain uh, orbitals or certain periods, certain energy levels, if you will. It can only occupy fixed orbits within the atom. So these were denoted as energy levels. The lowest one being energy level 1, and then going up successive order 2, 3, 4, 5, so on and so forth. The important idea here is that the energy is quantized, i.e., they can only have a specific amount. It cannot have. It can only have exactly two energy. It can't have 1.9 or 2.1. It can only have energy 1 or energy 2 or energy 3, and so on and so forth. And uh, that was this was really important because as we go on later, it described a certain phenomena that it described what atomic emission spectra were, and it sort of described them very well. Note that generally, as you go farther and further away from the nucleus, the energy levels become closer and closer together. So, energy one and the difference between energy level 1 and 2 is greater than the energy level difference between 3 and 4, and then 4 and 5 is even smaller, and so on and so forth. And they become infinitesimally small, such that the difference between them becomes infinitesimally small as you reach n equals infinity. Um, so generally, uh, now that we sort of have an understanding of what the Bohr model electron um, imposes, it's important to talk about electronic transfer. And when we go from the high energy level, we can excite an electron, which is essentially given enough energy to go to the higher energy orbit. And when we do that, it must absorb energy, obviously, because we have to input energy. But less obvious, maybe, is that when it goes down in energy levels, it releases energy. It must release energy, sort of. And you could think of that as it's going. It obviously, to get it up from a low to high energy level, we need to put energy into it. So therefore, if we go down, the opposite must be true. Energy must come from releasing low, come from going into the ground state, and it does. And we get this in the form of light energy. So what essentially happens is that when the electron goes down an energy level, it releases a photon of a certain wavelength, and we can actually um, track that down because it releases a photon of a certain frequency, which corresponds to a certain wavelength on the electromagnetic spectrum. So the electromagnetic radiation is a form of energy, which light is a part of. It's part of the continuous electromagnetic spectrum, and um, quanta, or light, or discrete bundles of energy, are called photons. And photons are technically massless, but they behave like particles, but they also have wave properties. It's part of what makes quantum mechanics really fucked up. But photons, as well as electrons, have wave and particle properties, and they are essentially both. So some of the wave properties of photons is that they have a speed, they have a wavelength, they have a frequency. The speed, it's pretty obvious how fast it travels. Wavelength is the distance between two consecutive crests, or more aptly put, it's the distance traveled during one full oscillation of the wave, and the frequency is the number of oscillations per second that occur in each second. So they're given the frequency of hertz, and they're related by this equation here: c equals wavelength times frequency. They're inversely proportional. Um, Wave number, that's just how many wavelengths fit in 1 centimeter. What makes a photon a particle, however, is that they exist in discrete bundles of energy called photons, and they travel much like a particle would, and if you go on physics and you study what is it, the photoelectric effect. Essentially, what happens is that they behave like particles because they displace. They when they bump into valence electrons in the middle, they displace them and they cause it to ionize. Whereas a wave would not do that. So that's sort of an example of particle properties a photon has. However, what you're expected to know is that the frequency and the energy of the photon are proportional to each other, where the constant of proportionality is called Planck's constant, which is a value of that. That's given in your data booklet, don't worry. White light is a mixture of all the different colors of light, and the way you can do that is you can put it through a refracting prism, and each wave color will refract at a slightly different angle because they have different wavelengths, so they'll refract at a slightly different angle and form a nice little rainbow you see here. Now, what does any of that have to do with what does anything we talked about here have to relate with anything we did? Well, now this is where we get to that. So the atomic emission spectra is sort of that. When you put energy into a gaseous sample of an atom, you excite the electrons in it, and causes them to go from low to high energy levels. But then when they come back and they go back to the ground state, what we call the lowest main energy levels that they can occupy, they will release energy. And like we said, this release of energy corresponds to a certain color of light that we actually see. And what we can see here is that the screen here is mostly black, but we can clearly see here bands that are red, blue, green, blue, violet, and these correspond to different electronic transitions or different energy gaps between the energy levels, the gaps of energy between the energy levels. So in topic 12, I believe, you actually do calculations with this stuff, but for now, you just need to understand sort of the concept behind it. So I believe, for example, this is, I believe for all the visual, for the ones in the visual spectrum, I believe they go down to energy level n equals 2. So this corresponds to a photon from energy level 3 to 2, 4 to 2, 5 to 2, 6 to 2, and so on and so forth. So this came from energy level 3 down to 2, and the reason I know that is because it's just a rearranging of the free rearranging of some of the equations we saw here. Let me go back. So we knew that E equals HF and C equals F lambda. Well, I'm just going to rearrange this one to get F, so C over lambda equals F, and therefore I can rewrite this as E equals H times C over lambda, and therefore I can get that E is inversely proportional to wavelength. So, in other words, the high wavelength stuff will have low energy. So, and wavelength, as you can see here, the wavelengths here are clearly labeled. So violet has a wavelength of 410, and that's the smallest here. So therefore, must mean this is of a high energy. So, and since this is the lowest one here, I'm saying that that's 3 to 2, and then 4 to 2, 5 to 2, 6 to 2, and so on and so forth. That's sort of how I'm deriving it as I go. And as you can see here, this is the Lyman series at n equals 1. This is in the UV. This is in the UV range of the electromagnetic spectrum. So as you can see here, 1 to 2, then 2 to 1, 3 to 1, 4 to 1, and 5 to 1. And notice here how they eventually converge to one particular wavelength. That's going to be important for the higher levels. If you're in the standard level, that's pretty simple. So, yeah, that's it. Thanks so much.